Welcome to the Module 3 on finite difference method. In the previous module, we had discussed derivation of governing equations for fluid flow, which is the first step in the numerical simulation using computational fluid dynamic techniques. And this is the first module on numerical methods, which is based on finite differences. So we would focus primarily on finite difference methods and its applications to different order of derivatives. So module outline is we will first start off today with basic methodology of finite difference method, and then we will have a look at how do we derive finite difference approximation for first order derivative, next finite difference approximation of second order derivatives, and applications of finite difference method to scalar transport problems. In today's lecture, we would focus on finite difference method, its basic methodology, and the notations which we would use in subsequent lectures. So now let us see what is finite difference method, a brief look at its history. So this is the oldest method for numerical simulation of partial differential equations. In fact, it dates back to 18th century and credited to Leonhard Euler. And the two methods which is still referred to by his name, forward Euler and backward Euler method for initial value problems. Both of these methods are based on simple one step difference approximation of time derivative, and we will have a detailed look at both of these methods when we come to time discretization aspects. Now this is one of the easiest methods to use for simple geometry. In fact, this finite difference method started off for solving partial differential equations on rectangular geometries, and that was cited as one of the basic limitations of finite difference method. But today we would just say that that's no more the case, and it can be utilized for solving problems on any type of geometry. And starting point is the conservation equation in differential form. This is what we had derived in the previous module, and we would use the techniques which we learn today for difference approximation today and in the next few lectures, difference approximations of the derivatives in our governing equations, and that would be used in obtaining a discrete form for numerical simulation. What are the attractive features of finite difference method vis-a-vis other schemes? It is easiest method to use for simple rectangular geometries. It is very easy to formulate, very easy to derive difference equations starting from the partial differential equation for any problem, and writing a computer program in any language translating our difference formulation is straightforward. In fact, so much so that today we routinely give it to our undergraduate students to write computer programs for solving heat conduction problems and fluid flow problems based on finite difference method. But one of the limitations which was cited earlier was that this finite difference method is primarily suited to simple rectangular geometries, because the method is based on the use of local Cartesian grids, but that is no more the case. In the beginning, to overcome this limitation, people used for complex geometries what we call body fitted grids, but today in the recent developments based on what we call the concept of immersed boundaries that had left behind the mapping which is required in boundary fitted grids and its limitations altogether, and we can use simple Cartesian grids for modeling any complex application. This point we would elaborate a little later. Other advantage which we have got is we can use domain decomposition based solvers if you are dealing with very large scale numerical simulation, which we have to routinely do for the solution of industrial problems, specifically the problems which involve turbulent flow. Now the whole problem cannot be solved on a workstation or a single computer, and we have got to use massively parallel computers for numerical simulation. And for this parallel simulations, we normally use what we call domain decomposition based approach, and finite difference method is one of the easiest to adopt to this domain decomposition approach. Now let us have a brief look at the application of finite difference method to problems in complex geometry. Method for complex geometries. So, I mentioned two approaches. The first one is what we call use of boundary fitted grids, boundary fitted grids. What do we do in this approach is, suppose we have got an arbitrary domain and we have somehow got to map it to a rectangular domain. So, let us choose these points 1, 2, 3 and 4. So, each one of these 1 to 2, that becomes one side, 2 to 3 is another side, 3 to 4 is another side, and 4 to 1 is another side, which has to be mapped. Okay. We have to obtain a mapping so that we can map it to a simple rectangular or a square domain. Let us call the coordinate system here by capital X, Y, and the coordinate system which we had for usual physical space is small x, y. So, each point is mapped. Let us say 1 goes to 1 prime, 2 goes to 2 prime, and so on, 3 prime and 4 prime, and this square domain which we have got, square or rectangular domain, this is what becomes our computational domain. Over which our finite difference equation has to be solved. So, what do we do in this case? Our partial differential equation which we have got, that has to be modified. So, we have got our modified PDE using mapping transformations. There are two problems associated with this approach. The problems which we had is generating a suitable map, a suitable mapping for an arbitrary complex domain, arbitrarily complex domain. So, this is not a straightforward task, it complicates the things, numerical solution quite a bit. And the second problem was handling of boundary conditions. This is not as complicated as the first one, but nevertheless the transformation from physical domain to computational domain, it makes the boundary conditions a bit complex. Okay. So, these two difficulties did put certain constraints in the application of finite difference method to the problems in complex geometries. But nevertheless, this approach was used very often in 1980s and 1990s. There is yet another approach, FDM for complex geometry. Our second approach is based on what we call immersed boundary method. Immersed boundary method, or in short we use the acronym IBM. So, the name itself implies what we have to do is we have to immerse our arbitrarily complex domain into a simple rectangular domain. So, we would use, this is based on simple Cartesian grids. So that means we do not have to use any mapping, no mapping required. So suppose we had our arbitrarily complex domain. All that we do is we just immerse it into a rectangular grid. So this is our simple rectangular grid. Then the question arises, how do we take care of these complex boundary segments which do not align themselves with these Cartesian grids? So here curved boundaries are taken care of by introducing forcing functions. Now these forcing functions are very similar to boundary forces, similar to the boundary force similar to the body force terms. And that is all we have to do. So introduce this term in our governing equation. Now that governing equation could be that of momentum or energy equation. So this method was proposed long ago by Peskin in 1972 for what we call today as biofluid problems. So naturally, when we are dealing with, let us say, the blood flow in our arteries or heart, we are dealing with fairly complicated geometries, and we can easily, now what Peskin did was immerse that complex domain into a simple rectangular Cartesian grid, take care of the complex boundary parts by introducing forcing terms in the momentum equation, and solve the problem. Now this is one of the most fertile areas of research today, so most active research areas. Research areas in CFD, and the beauty of this method is that using IBM we can solve not just the fluid flow problem, we can also solve fluid structure interaction problems, these can be handled as easily as solving a simple flow problem. And recently many new developments have taken place in the case of IBM, and we can use this IBM together with what we call can be used with adaptively refined Cartesian grids. What do you mean by adaptive refinement? Let us suppose in a specific region of the problem domain, we would like to have very fine mesh based on some error criteria, so that we can introduce. So, we can have grids of different densities in different domains to take care of the boundaries. Maybe we can have a fairly fine grid close to the boundary, and these features are permitted in the context of immersed boundary method. Now, let us have a brief look at the advantages which FDM offers in parallelization. So, here we can use a simple rectangular decomposition of a problem domain. Take for instance a simple rectangular geometry. Decomposition for a complex geometry would be fairly similar. So, this is a big problem domain omega. Now, this domain can be decomposed in smaller subdomains. Let us call them as omega subscript 1, omega 2, omega 3, omega 4, omega 5 and omega 6. Now, each one of these subdomains, they can be mapped to a separate processor or separate CPU of a massively parallel computer. So, we do not have to make use of any advanced or fairly complicated mesh partitioning algorithms in this case. We can simply decompose a problem domain in small subdomains. We can have different types of Cartesian grids or grids of different density on each subdomain, and the interface information can be easily passed on from one processor to another as a part of solution process. Yet another important aspect which is permitted by this finite difference and domain decomposition based approach is, so we can have domain decomposition based multi-grid solvers, which are very efficient, and in fact they scale with the order n, where n is the total number of nodes, and generation of what we call a sequence of grids, a sequence of hierarchical grids required in multi-grid algorithm is very simple or very straightforward in case of Cartesian grids of finite difference method. So, these important advantages or attractive features of finite difference method today make it one of the most widely used numerical discretization scheme for simulation of very complex turbulent flow and fluid structure problems. Now, before we proceed to details of the method, let us have a look at what we call conceptual procedure, that how do we solve a given fluid problem using finite difference method. So, the first thing which we say is discretize the solution domain by a grid, that is our continuum problem is represented by a set of discrete points which we will call nodes. We will elaborate on this point a little later. And next what we do, at each grid point we approximate the differential equation using finite difference approximation of derivatives. Now use of this finite difference approximation for the derivatives converts our partial differential equation into an algebraic equation at each grid point. We repeat the same exercise at boundary grid points as well, but the boundary conditions are fairly simple. Let us have Dirichlet type where the solution variable itself is specified, we do not have to do much, but if there are any derivatives in boundary conditions, we replace or we approximate these derivatives by using one-sided finite difference formula. So now with these two steps we have now converted our partial differential equation or boundary conditions into discrete algebraic equations at each node, interior as well as boundary nodes. Next step, what do we do? Collect the algebraic equations obtained at the interior node as well as boundary nodes to form a system of algebraic equations which will usually be a sparse algebraic equation, and we just need to solve this resulting algebraic equation to find out the values of the problem variable at each grid point. If we are dealing with time dependent problem, then instead of an algebraic equation we would get what we call a discrete system of ordinary differential equation, and that has to be further discretized using a time discretization scheme which we will discuss in future module. And once we have obtained the solution values at each of the grid points, obtaining solution at any point in the interior of the domain is very simple. We can obtain the derivatives of the variable. Let us say we are dealing with flow field, we have got the velocity values and pressure, we can obtain the stresses at any point in a solution domain by numerical differentiation and interpolation process. So this is our simple conceptual procedure. Now we have mentioned grid. Now let us have a look at few more things. Notation, the grid which we see. What are the properties of the grid? The finite difference grid is locally structured. What do you mean by this term structured? It simply means that each grid point, which you would also call node, may be considered as the origin of a local coordinate system whose axis coincide with our grid lines. Grid lines represent the lines or curves or maybe surfaces in a space at which a certain coordinate value remains constant. So suppose you have got grid lines of same family, the properties are two grid lines of the same family do not intersect, and the next property of the grid is that any set of grid lines belonging to different families intersect only once. So let us have a look at a typical two-dimensional finite difference grid on its rectangular domain. So we have used m grid lines in x direction and n grid lines in j direction. Each node can be identified by a pair of indices corresponding to the intersection of the grid lines. For instance, this particular node, it belongs at the intersection of x is equal to xi grid line and y is equal to yj grid line. So we will use a simple symbol I comma j to denote this finite difference node. Okay, so what we do, each node is identified by a set of indices which are the indices of the grid lines that intersect at it. Thus node I, it represents the grid point x is equal to xi in one dimensions. Node I comma j represents the intersection point of grid lines x is equal to xi and y is equal to yj in 2D. That is what we saw in the previous slide. Similarly, node I comma j comma k represents the intersection point of grid lines x is equal to xi, y is equal to yj and z is equal to zk in 3 dimensions. Now there are some shorthand notations which we use in our grids. Let us have a look at these two shorthand notations which we will for grid spacing and function values at grid points. So, our shorthand notations the first one to denote what we call grid spacing. So, let us have a look at simple one dimensional grid space or one dimensional line here. These are our grid points. Let us say a generic grid point we denote by index I, which corresponds to x is equal to xi. The next grid point we use symbol I plus 1, this corresponds to x is equal to xi plus 1, and similarly I minus 1, which corresponds to x is equal to xi minus 1. Now, how do we represent these spacings? We use a symbol capital delta to denote the difference between these. So, this x of I plus 1 minus xi, this denotes the spacing between grid points xi plus 1 and xi, and we adopt a simple convention, we call this as delta xi. So, xi plus 1 minus xi, we would use a shorthand notation xi. Now, following this notation, the difference between ith grid point and one to the left of it, that is x is equal to xi minus 1, that is our I minus 1th grid point, xi minus x of I minus 1, we will call or we will denote it by delta x I minus 1. Similarly, the same convention we can extend in multi-dimensional space. So, in multi-dimensional space in other two directions, we will use the symbol j to denote our y lines. So, yj plus 1 minus yj, this grid spacing would be denoted by delta yj, and let us use subscript k to represent an index in k z direction. So, zk plus 1 minus zk, we would use the shorthand notation delta zk. Okay, the next is shorthand notation for function values. The first, in the case of one dimensions, at point xi for its generic function f of xi, we would use a simple shorthand symbol f subscript I. So, in our finite difference formula, that is what we would use. Similarly, in two dimensional space, in 2D, to represent the function value at point xi yj, we would use two subscripts to symbol f, I comma j. If there is no confusion, we can also simply write it as f of I j. This comma is mandatory in case if we are dealing with the slightly more complex indices for I and j. For instance, if we want to denote x of I plus 1 y of j plus 1, the function value here. So, now in this case we must use a separation by comma between the subscripts. So, f I plus 1 comma j plus 1. So, these shorthand notations make it very simple for us to write our difference equation in a compact form, and they also help us to transform or translate these formulae into a computer programming language. Now, let us see what do we do in 3D. 3D we will use 3 subscripts, that is f at xi, yj, zk. This we would represent by f I comma j comma k, or alternatively we can also write it as omit the commas in this case f I j k. As I illustrated earlier, this comma we would require when this indices are longer than one symbol. For instance, x f of x I plus 1, y j plus 1, z k. So, now in this case we have to use this comma separator between different indices, so f I plus 1 comma j plus 1 comma k. So, please remember these shorthand notations because we would use these in our difference formula very often. Next, let us have a look at grid types which we would normally encounter, which are fairly frequently used in finite difference approximation. We can have what we call uniform grid, and if the grid is not uniform, we would call it simply as non-uniform grid. So, what do we mean by a uniform grid? When we would say that a grid is uniform, if you are dealing with a one dimensional problem, 1D, a grid is uniform if spacing between each pair of grid points is the same. So, if you have got a set of grid points, let us say I plus 1, I plus 2, I minus 1 and so on. So, we can simply say that x I plus 1 minus x I, this is equal to x of I minus x of I minus 1 is equal to x of I plus 2 minus x of I plus 1 and so on. Each of these differences are equal, or using our compact notation we can write this as this delta x I is equal to delta of x I minus 1 is equal to delta of x I plus 1 and so on, and we can use drop this subscript to delta x I, we can simply write this as delta x. So, now we have got a uniform grid spacing of delta x, and if this were not the case we will call the grid as non-uniform. In multi dimensions, the grid would be called uniform, if spacing along each grid line is constant. Now, this constancy does not mean that we have to have same spacing along each family of grid lines. All that this definition requires is that our delta along each x line separately, that is delta x I is equal to delta of x of I minus 1 is equal to delta of x I plus 1 and so on. This would be equal to delta x. Similarly, delta of yj is equal to delta of yj plus 1 is equal to delta yj minus 1 and so on, and it is equal to a constant spacing delta y along the j grid lines, and similarly delta zk equal to delta of jk plus 1 delta zk minus 1 and so on, and it is equal to a constant increment or spacing delta z. So, that is what we mean by this uniform grid in 3 dimensions. There need not be any correlation between delta x, delta y and delta z, they can all be different. And as a corollary, a grid is non-uniform if it is not uniform. Okay. Let us come to the basic concept of finite difference approximation, and as you can easily guess, it is based on what we are using approximation for. What we are using approximation for a derivative. So, let us go back to the basic definition of a derivative which we learned in our calculus class. The derivative of function f with respect to x at a given location xi, del f by del x at xi. How do we define it? We define as limit of delta x tending to 0 f of xi plus delta x minus f of xi divided by delta x. So, that is the basic definition of our derivative. Now, if you want to obtain an approximation to this derivative, what we can do? That approximate value of derivative can be obtained from the finite difference expression, where we do not let delta x become 0, we will take a finite delta x, that is why we use the term finite difference. So, delta f by delta x, that is derivative of f with respect to x at point xi, this can be approximated by the simple finite difference, the value function f at point xi plus delta x minus f of xi divided by delta x. Or if you use a compact notation for these function values, we can write it as f of I plus 1 minus fi divided by delta x. Now, this is one approximation which is frequently referred to as forward difference approximation. Why we call it forward? Because we have used a value of the function at a point to the right of point x is equal to xi, that is what this value fi plus 1 means. Now, there is a geometric interpretation which we have in this case. Let us have a brief look at that geometric interpretation for a function. Suppose we take a generic function, this is f of x, and this is the curve which represents our function f(x). We want to find out its derivative at point xi. So, derivative is given by the value of this tangent. If you draw a tangent to this point, the slope of that tangent, that is what gives us the derivative. Now, suppose we take this point xi plus 1. So, the expression which we saw f of xi plus 1 minus f of xi divided by delta x, this difference is delta x. Now, this is given by the slope of this line. So, initial tangent, let us say at point P was AB. The forward difference approximation is basically the slope of this line A prime B prime. The same thing we can say that, look, if instead of taking a point to the right of point xi, we can choose one towards the left, let us call it xi minus 1. Okay. And if you use the values here, these two values, let us join this point and draw a different line, let us call this A double prime B double prime. Slope of A double prime B double prime that is f at xi minus f of xi minus 1 divided by delta xi minus 1. Okay. And this is what we refer to as a backward difference approximation. Okay. So, that is geometric meaning of the slopes, and it is also very easy if we take the slope of these 2 points here at x is equal to xi minus 1, and let us join these points, let us call them as S and T. We can clearly see the slope of this line ST is a pretty close approximation, it is almost parallel to a tangent AB, and later on we will learn that the so called central difference approximation, which we can get by using the values on both the sides of our point P, that gives us a much better approximation of the derivative compared to a forward difference or a backward difference approximation. Before we conclude today's lecture, let us have a look at few useful definitions which we would frequently use in coming lectures. We will look at 2 definitions: the order of magnitude, truncation error, and order of accuracy of a particular approximation. Now, this order of magnitude, this is what we would use when we specify the truncation error or the order of accuracy. So, what do we mean by order of magnitude? Let us say that we have got a quantity gx, it is a function g of x, it is said to be of the order h to the power m, where m is greater than 0. We alternatively write this as gx tilde o, this capital O is used to represent order of, so o h to the power m if limit h tending to 0 gx divided by h to the power m is equal to L, where L is a finite quantity. Now, this definition we have taken from the book of Neogi et al, and it tells us when we would say that gx is of the order OHM. Next, the truncation error. We just saw that we can represent an approximation of the derivative by using, let us say, finite differences. How much error we have committed, that we can obtain from Taylor series expansion. So, truncation error represents the sum of the terms in a Taylor series expansion which were deleted in obtaining the approximation of the derivative. So, let us have a look at what we just did and see what do you mean by this truncation error in the case of forward or backward differences. For the sake of simplicity, let us concentrate on forward difference on an uniform grid. So, f at point xi using Taylor series expansion, we can write it as, so Taylor series expansion at x is equal to xi, that gives us that f of xi plus 1, this can be written as f at xi plus delta x times del f over del x at xi plus delta x square divided by 2 del 2 f over del x square plus delta x cube by 3 factorial the third derivative of f with respect to x at point xi plus so on. If we rearrange the terms, that is what we get for this del f by del at xi so it is f of xi plus 1 minus f of xi divided by delta x minus the higher order terms which we had. So, we will get this delta x times del 2 f over del x square xi plus del x square divided by 3 factorial del cube f over del x cube xi plus so on. So, if you want to use an approximation, this forward difference approximation, we would retain only the first term on the right hand side and the remaining this terms in bracket we can say that this is what is our truncation error. Okay, so truncation error basically gives us the higher order terms which we have omitted in obtaining our finite difference approximation of the derivative. Next we would use the term very often that a certain difference scheme is such and such order accurate. What do you mean by that? It is simply related to truncation error. If the truncation error of a finite difference approximation is of the order of delta x to the power m, then this difference approximation is said to have the accuracy of order m, or we use alternative description as that this difference scheme is mth order accurate. Now there are various approaches which are used for approximation of derivatives. So I have just provided list here of most popular approaches. The first one is Taylor series expression, the second one is based on polynomial fitting, the third one is based on Paré approximants. We can use difference equations and there are many other approaches. We would focus in our lectures, next few lectures, on these two approaches, Taylor series expression or expansion and polynomial fitting. Now remember that when we derived our conservation laws or governing equations, we had mostly first order and second order derivatives. The first order derivatives we got in convective terms, and on the diffusive terms on the right hand side we had second order derivatives. So we would primarily focus on finite difference approximation of first and second order derivatives in our next few lectures. We will stop here and we will continue our discussions on finite difference approximation of first order derivative in the next lecture.